that's taking 13 microseconds. I see 7 microseconds. And if I compare that, matrix multiplication here is taking 5 microseconds, 5 microseconds. Actually, like the same amount of time that it takes Python to like define a class for doing our entire matrix multiplication. So that's bad. Hello, everyone, and welcome back to another Modal webinar. I'm your host, Charles. I work on DevRel at Modal and build Gen AI and data and ML apps on top of Modal's infrastructure. So what I wanted to cover during today's webinar is how to profile and debug the performance of GPU applications running on Modal. And we'll do like a little high level thing about like why that matters and some like just like high level kind of tips and tricks. And then we'll dive into a specific example and some code. When we go through the code, we're going to be working through this example in Modal's docs on tracing and profiling PyTorch programs that use GPUs. And as part of that, we'll see how to generate a trace like this one that shows what happened while a program was running on CPU and GPU, and then also how to host TensorBoard, which does not just showing you those traces, but also kind of calculating a bunch of high-level summary metrics and even providing some performance recommendations. So we'll show how to do all that on Modal, like just some high-level things about, making GPUs run really, really fast on Modal. So number one, like why should you care about GPU performance at all? Like why is this important? The primary reason why this comes up so often and comes up more often than it does for CPU applications is that GPUs are actually, really expensive, high performance computing devices, especially like the H100s available on Modal. This is not like an easy to use device, right? Nobody really like wakes up and says, you know what, today I'm going to have some fun. I'm going to program something to run on GPUs. The GPUs are generally chosen because the general purpose processors that we use for everything else, for running databases, for managing files, for running user interfaces, those general purpose processors, for whatever reason, can't meet our performance or performance per dollar targets. And so we need this specialized accelerator in order to make our programs run faster. But what that means is that when you are programming a GPU, performance is basically always part of the desired behavior. Like you have chosen GPUs because you want to make things go faster. This makes performance like part of the program specification. It should be performance, it should be faster than it would run on a general purpose processor. It needs to be faster per dollar often, and GPUs are more expensive. So now you might need a 10x speed up or a 100x speed up over CPUs for it to make sense to use a GPU. And then if the not hitting your performance targets was enough to make you consider this accelerator and consider all this extra programming effort and tooling effort to get things to run on GPUs, it's probably the case that this is something where that like really matters. And so it's not just that you want to hit some like minimum performance or performance per dollar target, but often this is something where like no amount of performance is performant enough. You could always run faster. Chat interfaces, for example, up to about a couple hundred milliseconds response time, you really want to make the inference run faster. And then even if you hit below that, it's like, oh, well, if I could run 10 models at once and then respond to the user in 400 milliseconds, I could actually make use of that. I could do some inference time compute scaling tricks or something like that. And so these are frequently cases where like you just really want to squeeze all the performance that you can out of the application. And so you really want to check the performance, the latency, and the throughput of your application running on the GPU. I'm going to talk about a couple like kind of high level tips that I have for debugging GPU performance from having done a lot of training of neural networks, running inference for neural networks. Primarily those workloads. I think I haven't done very much like graphics stuff. Ironically, for somebody who uses graphics processing units so much, the focus is more on these ML workloads that tend to be what people are running these days on Modal's platform. And like the number one high level thing is that the more that you can measure and the more that you can see, the more effective your debugging is going to be. Just want to walk through quickly this kind of flow chart for how I go about GPU performance debugging. When I run something, I've grabbed some open source libraries, I've compiled them together, I put them up on Modal GPUs, and now I'm running them, and it's like, oh, you know what? This feels slow. This is not fast enough for whatever my target is. So the first thing that I do is I check GPU utilization. This is reported by NVIDIA SMI. It's available in Modal's interface. GPU utilization is the fraction of time that a kernel is running on the GPU. And that's like a very base, kind of check of am I actually using the GPU at all? It doesn't check am I using it super well? It's just am I using it most of the time that the hot loop of my program is running? And frequently the answer is going to be no. And kind of the primary cause here is that whatever CPU program is driving the execution on the GPU, that thing is getting in the way of execution on the GPU. It could be the Python part of PyTorch, or it could be the rest of PyTorch or whatever program you have driving your execution. You can take a look at the traces and sort of see whether what's happening is that the GPU is waiting on operations that are happening on the CPU. The GPU has to wait for operations to finish on the CPU for whatever reason. And if you can pull the CPU out of the loop and make sure that the CPU is not sort of blocking forward progress, that's a great way to fix those problems. You might just see sort of Python overhead, the things that PyTorch or a similar program needs to do in order to sequence work on the GPU, that it's getting behind the work that's running on the CPU instead of running on the GPU, rather than getting ahead of it due to Python overhead. So tools like Torch compile, reduce overhead in reduce overhead mode, or similar can kind of get Python overhead out of the way. Another one, VLLM, the LLM inference server, has a low overhead HTTP server based on 0MQ. If you can sort of get rid of a lot of Python overhead with that. And then lastly, you might see oh no, actually it's just that, there's just not enough work for the GPU to do. I'm launching kernels, they're running, but they don't run for very long. And so there's just nothing to be done. In that case, usually the best thing to do is to increase your workload, because turns out that actually increasing your workload, doubling the number of samples you're generating from a language model, doubling the batch, running 3 or 4 replicas of the model, because you are underutilizing the GPU, actually adding those things doesn't doubling them doesn't double your cost. It multiplies your cost by 10%, or maybe is not noticeable at all. Because things are executing concurrently, and so there's no additional work or no additional latency penalty or throughput penalty to increasing the workload size. So this is something you can find out by looking, if you can discover that you have that opportunity in part by looking at traces and profiles for low utilization applications. If the GPU utilization is high, the next thing that I'll check is if the GPU's power utilization is high. So this is what fraction of the GPU's power budget in watts are we actually using? And this one is just a little bit of a gut check, just because the GPU utilization metric can be high, even though you aren't really thoroughly using the GPU. You've got kernels running, but those kernels are maybe only using a small fraction of the streaming multiprocessors on the GPU, or they are they're doing communication, but they aren't, they're blocked on communication and slow for that reason. So power utilization, because GPUs are fundamentally limited by power draw, is a good double check on GPU utilization. That's also reported in the dashboards for your Modal apps. So you can check that really quickly before you go into the deep identification of bottlenecks and tracing and profiling. That in the end, if you see that your power utilization is low, then you're probably just going to need to do some tracing and profiling anyway. But it's good to know ahead of time that that is the problem that you need to debug, and not not the sort of alternative here, which is that you need to identify which operations running on the GPU are actually your bottleneck. Maybe it's a matrix multiplication, maybe it's an attention style calculation. Who knows what it might be? You need to find what that bottleneck is. That bottleneck, it could be loading things from memory, it could be doing compute, and you can find that out by doing some tracing, profiling, counting some performance numbers, and doing a little bit of like maybe some napkin math to figure out what those bottlenecks are. So just to double click on that point about watching power. So on the left and right here, I have two different screenshots from a modal dashboard showing two applications running on GPUs. On the left, an application running on an A10. On the right, an application running on an on an H100. And though both of them show super high GPU utilization, so if you were to NVIDIA SMI and look at the that utilization percentage, you would see 100%. But one of these applications is making no forward progress, and the other one is like really chunking along. So the one on the left on the A10 is making no forward progress because it's deadlocked, in fact. That like it's actually two GPUs talking to each other. They're both waiting on each other, but because they're both waiting on each other, nothing happens. And one sort of symptom of this problem is this low GPU power utilization here, where the power utilization is in the middle range as a fraction of the power limit of the GPU. And on the right-hand side, we have what this looks like for an application that is actually making rapid forward progress. This one is just running matrix multiplication on an H100, just really big matrix running for a while. And that is the sort of thing that really makes effective use of the GPU's compute units. And that is what we want. Matrix multiplication is the core thing GPUs do. When we run anything on GPUs, we want it to look as much like just running matrix multiplication as we can. And so what we can see is, yeah, we have that high GPU utilization. That means that we are running kernels all the time, just like we are in the case where it's not running well. But in this case, we can see that the GPU power utilization is up between 80 and 100%. I think it is difficult to run a GPU at 100% power utilization all the time, at least in my experience with cloud GPUs. I think part of that may have to do with just the way that they have the GPU set up, their ability to egress heat from a giant collection of GPUs, not just the one that you are running. But just ballpark numbers for these are 70% and higher is looks like good numbers. I think for GPU utilization, 95% plus is pretty good numbers. It can be hard to get it below that. So a note from Fatih in the chat here, you can set TDP caps on NVIDIA GPUs. Check out this article here. So this actually is something that you can modify. There are limits to that. There's a reason why the thing is designed not to draw too much more power in terms of creating too much heat. So that's actually something that we also log down here in your modal dashboard, this GPU temperature here. So the kind of temperature cap on an H100 is I think 80 degrees Celsius, maybe a little bit more than that. And the effective cap, the kind of point at which actually the increased heat is starting to cause the beginnings of problems. It's not so high that the sort of GPU's firmware steps in and says, whoa, let's cool this thing off. In that area, you might start to see the beginnings of decreased performance. For example, somebody on Twitter was pointing out that at the temperature that I'm showing here in this diagram in the low 70s, you actually start to see increased error correcting code failures, bits flipping and not being set to the right values. That's another reason maybe why the power utilization percentage is capped lower than 100% here, to try and control that GPU temperature to keep it in the range where it's actually optimal. So if you really in the end, just to step back from analyzing all of these metrics in detail, these are sort of correlated metrics. They correlate with a highly performant application, making really great use of the GPU, but they aren't the thing that you actually care about, right? The things that you actually care about are floating point operations per second, latency to complete a request, throughput of requests. Those are the things that you actually care about, and these are sort of like these are more like gauges, that kind of like help you at a high level understand the system to know whether you need to intervene and like what that intervention might look like. But they aren't a like substitute. They're just like they're generic and they're like easy to implement for like everybody. Like everybody running something on Modal gets these charts for free. But other kinds of like detailed profiling and measurement are need to be like kind of implemented by hand per project, or they have overheads, so you don't want to run them always. Yeah, but these are just sort of like your signposting guide to get those like detailed metrics that allow you to understand both like the low level and high level things that you truly care about, which is like floating point operations per second and memory reads at the low level, and requests per second and response times at a high level. You want a profiling and tracing tool for the low level metrics, and you want a like load testing tool of some kind for the high level metric. Showing a couple of my favorite tools here. PyTorch has like these built-in profiling tools built on top of NVIDIA's qt. That's the like very lowest level interface that like increments performance counters, like tracks events. That's like close to the hardware, and then like PyTorch has built things on top of that to give you like a better experience for when you're doing things with PyTorch programs. I will say that this tooling can be a little bit rough. It's like a lot of this. I think a lot of the like top teams are like building these things in house and not open sourcing them. So the open source tooling has some like kind of pain points or limitations. Like for example, the memory visualizer and the like memory profiling stuff in PyTorch, I think is like marked as experimental. Like uses some like private variables, things prefixed with underscores, which never makes you does not inspire confidence when using them. And every once in a while, I'll go back and start using a workflow I was using previously, and it'll be like deprecated. So you kind of got to watch out for these things. It's a little bit like high effort to maintain a really a good usable stack, but it has been getting better over time. I would say like a couple of years ago, these things were very, very jank, and they've been getting quite a bit better. But yeah, so I have the memory profiler from PyTorch up here showing like the slab allocator running in the VLLM instance. And then this PyTorch profiler, this is the one we're going to spend most of our time with today. This is showing like the execution of a language model in VLLM. And you can kind of like poke around and see where there might be gaps, what operations are taking a long time, sort of detect sort of maybe surprising behavior of your program that wasn't in your mental model of what is happening. We'll do quite a bit of that in just a second. And yeah, for load testing, I like Locust, and you can find an example of how to do that if you go to our docs and check out the VLM inference example. Check that out. Not just the code in that example, but some extra code linked from it on GitHub shows you how to do this kind of like load testing of that VLM server to get like as users come in, what happens. And this is particularly nice for once you deploy your application on a platform like Modal that also has like auto scaling behavior that you need to tune on top of just the CPU stuff. The load testing is really great for seeing, okay, what is going to happen when I trend on Hacker News and 1,000 people come in at once. Let's dive in and take a look at what using those on Modal looks like. This is our docs page for this example. So all of our examples in our documentation, they have these nice rendered web pages, but they also have like matching code on GitHub so that you can like read these things when you just want when you just want to understand how something works. And like maybe you just want to copy one like code snippet at a time. But if you want to like run it yourself, then you're going to need to like go on GitHub, get a hold of the code, and run it. So that's what I'll be doing from my VS Code instance here. So you can see this is that same thing. Like, we got the title up here. So these are just like, this is kind of like a markdown format inside of a Python file. And so what we're going to do with this example is we're going to take a modal function and we're going to wrap it in another function that like runs a PyTorch profiler on it. And so the reason why I wrote this example this way is to show you some like patterns that you can use specifically on the modal platform for like effectively profiling things. Just because like you can just like shell into modal instances and run command line tools the way you would with a server, a serverful platform. But it like part of the power of modal is being able to like actually do all this stuff serverlessly. And it's not always obvious how to do that. It took me a while to figure out like a really nice pattern for doing this profiling. So I wanted to kind of like share that with this example. Not just the general tooling like profiles, but also like how to map that stuff onto modal. So an example of some things that are nice for mapping that onto modal. We're going to save our the like traces that we generate from the profiler on a modal distributed volume so that we can look at them from different places. We'll use that to like read the traces from TensorBoard, a like totally separate instance running TensorBoard. And we will and then like it also means like, oh, this is stored. I don't need to worry about like, it's on my laptop. Let me go and grab that thing. It's like stored in this like distributed remote storage, kind of like, like an S3 type experience. So that's nice. And it's like pretty easy to configure. This is all you need right here, compared to how kind of painful that can be with AWS sometimes. Okay, let's take a look at the modal function. We're going to be profiling this stuff here that I'm kind of was about to scroll over. This is kind of boilerplate. There's some other videos on the YouTube channel if you want to check those out, or just other examples in the modal examples that sort of explain a lot of these things in more detail. Like, what are we doing here when we're like setting up our dependencies? What's this block doing? So I go into greater detail in those and some of the other videos, and we have more detailed docs on them, basically setting up the environment that the function is going to run in. And we want that to be the same, in the function that we're going to deploy, like when we run it in production, and then also when we're profiling that same function. So right here, this underutilized function, that's the function that we're going to be profiling. So let me just quickly show you what that is. So we're going to take this random matrix here, and we are going to multiply it with itself in a loop. And then I've done two things that we'll later use to like sort of intentionally set this up in a way to demonstrate how like what a like bad utilization, bad performance looks like. One is like this matrix is pretty small relative to what GPUs are capable of. So this is not really enough work to keep the GPU busy. And then second, you'll see here inside of that loop, I'm actually defining a Python class in order to like add it to some like record, something that was like logging or monitoring this this matrix multiplication. That's what this is meant to mimic. Like maybe this is your like data pre-processing step in a real application, or maybe it's it's like logging or or like communicating requests back out to clients. Like something as simple in that loop as like just creating a Python class can substantially slow things down. So we'll see that. And then lastly, at the end of this, I do like a host sync. So I send some data from a tensor to the CPU. That's to make sure that like when this thing runs, it runs all of this to completion. And rather than like just like zooming forward and maybe like running many calls of this function before the GPU finishes running. So putting a host sync like this inside of a loop is actually also a good way to slow a GPU program down. You're like now the CPU needs to wait for the GPU to finish, and then the GPU can start running again. And so that's bad, and you want to avoid it when possible. Run things concurrently. This guy here is meant to sort of mimic what a modal, like a function that you would actually be deploying. Like this is the equivalent of something that would like run inference for a model. So we want to wrap that with a profiler. So we're going to write another modal function that runs that other function, but with the profiler wrapped around it. And so this in particular, like PyTorch's profiler is very like kind of code forward. You don't like call your application from the command line with like wrapping it in a profiler. Um, and so, and that can be useful because you can like really kind of like nail like the specific function call that you care about and like tightly trace and profile it. So because of that, what this looks like is we have this kind of like wrapper function here that runs the profiler. And then if you zoom in, what it does here, right here, is where we're actually calling the function that we want to profile. Right here is like function.local. That's like calling the same function that we defined above, in this case, like underutilize, running it in the same container that this profiling job is running. So rather than like you could, if you want to call a modal function, you can either do it that way where it runs in the same process that is, or like on the same machine that is invoking it, or you can like kick it off to a remote container. So even functions running on modal can like call modal functions running in other containers. But that's not what we're doing here. We're keeping it inside the same container. Yeah, calling the function locally. So that means that this, like, if I were to call it remotely, then the like local, this like profiler would just be like, oh, you like called out, made some like gRPC or HTTP requests, and then like some stuff came back. It wouldn't be able to like introspect and see. So that's why we're doing this like local execution. So this pattern gives you the like full programmatic flexibility and integration of the PyTorch profiler at like the granularity of the individual functions you're defining on modal without needing to like shell in to run these things or edit your actual function code. There's a bunch of stuff in here that I added. Like this is meant for it to be like usable outside of this like demo example. It's something that you can like copy and paste. So that's why, for example, even though we're in this example, we only profile one function, this underutilized that I talked about. I wrote it to be generic so that you can pass in the name of a function and run that. And like that function doesn't really have very many arguments, but like, and I could have just written them out, but here I've like made it possible to like provide keyword arguments to run in that function you're calling, which is like, more realistic to what a function would actually look like, a function you're interested in profiling. So there's a bunch of this stuff here that's for that. I would say like, main things for like mapping general profiling workloads onto modal are that function.local trick that I described, the fact that we're saving things onto this tracer, saving these onto a remote volume. And then I'm also going to end up returning them locally. So it's saved remotely, and I'm just going to send it back as text here. Like it ends up being a JSON file. You see that here, that the output is a JSON file. So I'm just going to send that JSON as text back to the like anybody who calls this function so that they can save it and like make use of it however they want. Focusing a little bit more on Torch's profiler and the configuration of that Torch profiler, it's handled as like a context manager. So it's like with this profiler, do this stuff. You can provide a schedule of what kind of like what to do on multiple rounds, iterations, or in their terms, like steps of a schedule. So that's this bit here. So we're like looping over calling this function, and we are like stepping the profiler each time. This is nice because you can set a schedule that says like ignore the first couple steps because like maybe some things are warming up. Those first couple steps are doing like amortized work. The profiler itself has some overhead the first couple times it runs. And so like it's nice to just ignore a couple of those and say like, just show me the results from things after that. And maybe I want to accumulate statistics because there might be some variability. So that's done here. The default schedule with the default number of steps is just going to like skip one iteration, warm up the profiler for one iteration, and then steps is 3 by default. So we just capture one iteration of the function and we don't repeat this at all. That schedule just like grabs you like one iteration of the function that should be like relatively warm and representative of what it would be like to capture one in the middle of like many executions of this function. there's kind of like two pieces of Torch's profiler. It produces profiles, which is like averaged, like collected up, like how much time is being spent in different like function calls. Profiles are nice, and you can like read a lot of useful information out of them once you like spend a lot of time looking at them. But I actually prefer these traces. This like trace output is like just a collection of events, and you can just look at an execution and see what that looks like. It helps me like debug my mental model of the program to have a trace of its execution, and so I can see like, oh yes, this happens, then this happens, these things are happening concurrently, these things are happening serially. Like if you have a really good mental model of your program, those you won't need the traces as much for that. But like honestly, I think there's actually quite a bit of surprise possible with the asynchrony of Python to CUDA, and then also like the asynchrony within CUDA in PyTorch's stack. And so it's like quite likely that there's that a program that is surprising you by having bad performance maybe has a surprising behavior that you aren't properly mentally modeling. So these traces are really valuable for that. When you run stuff on Modal in sort of like a script style, as opposed to like running it via remote procedure calling style or running it via an API, you use these local entry points. So this local entry point main here is the way we're going to execute this. We just use modal run pointed at this script, and there's some arguments. You can pass help if you want to see a little bit more detail about what those arguments are. A lot of them just get passed on to the Torch profiler. Yeah, so modal run like this. We're spinning up some containers. We're setting up not just the profile thing, but also running the thing it is profiling. So yeah, this is printed out. Because I'm kind of zoomed in here, this table is a little bit messy. Maybe if I zoom out, you won't be able to necessarily read it, but you can see this is what the like nice clean output table shows you. I've organized it by how much time we're spending. And we can see most of our GPU time here is in matrix multiplication. So that's pulled out here. But then we see there's actually, I can zoom in a bit again because this is outside of the table. We see that there's actually quite a bit of time spent. So like CPU time is like 10 times longer than the CUDA time. So that says that we're spending a lot more. You want these two things to be about the same, that the duration of time that things are running on the CPU is about the same as the duration of time that things are running on the GPU. And so we have poor utilization. So I'm going to actually add one more argument that makes it a little bit easier to see. This with stack argument is going to add some extra annotations to our trace, so that we can see what's going on with it more easily. So it's been saved to a remote volume on Modal. It's also been saved here locally. So that's logic in the local entry point here for that. That's right here. Like we get the profile and then save it locally to a temporary directory. Okay, so let's copy that guy out. Yeah, you get this table rendered in the terminal, but that doesn't show you like what was actually happening on the device. Like you can't see the execution. You can learn to read these stats for things like, oh yeah, this is really big and this is really small. That's a bad sign. But like I find, yeah, looking at the actual traces way easier to figure out what needs to be fixed. So there's a great tool for this called Perfetto. So this is like a trace viewer. These traces are compatible with a bunch of the tracing tools you'll use for tracing things in like browser and mobile applications. So if you have the Chrome browser, Chrome has built-in tracing that can view these traces. This Perfetto UI.perfetto.dev has this Perfetto trace viewer with some extra nice features that you can just use for free. So just go to UI.perfetto.dev and load in your trace file. Let me walk you through what we are seeing in this profiler. So generally there will be some number of Python processes that are focused on stuff running on the GPU, and some for the CPU. Frequently with PyTorch, there's like just one for the GPU, and that thing running on the GPU, you can tell it has a stream rather than a thread, a CUDA stream, as opposed to like an operating system thread or process. And so like looking for that stream is how you know that like this is something running on the GPU. Oh, that's nice. Oh yeah, I can pin that stream so I can like easily compare it to other things. Nice little features of Perfetto. So the nice thing with, yeah, now that that's pinned, we can see like what's happening on the GPU there. And these little like mustard colored blocks here are things executing on the GPU. And if you click on them, I think you might have to flip a setting that I just happen to have already on. You can see the relationship between CUDA launch kernel invocation. So like PyTorch or your CUDA program, CUDA C program on the host saying like, hey, I want to run a kernel, to like a link to like what kernel did it actually launch on the GPU. So here, these are like pretty nicely lined up, but that's not always the case. And actually, frequently, that's very much not the case when things are going well, because the CPU is saying, oh, I'm going to want to run this on the GPU. I'm going to want to run this on the GPU. I'm going to want to run this. And the GPU is like way behind, because it's like crunching through a lot of work. In sort of the same way that like, you know, an engineering manager sets out a roadmap and says, we're going to build this, we're going to build this, we're going to build this. And then the engineers have to take a long time to build those things. It's bad if the engineering roadmap falls behind the engineers, which is kind of what's happening in this scenario, because you can see this kernel finishes running long before we get to the point where the CPU is like ready to launch the next kernel. And so the symptom of that is low utilization. So kernel utilization, that high-level metric that NVIDIA SMI reports that you can see in your modal dashboard, that is basically the fraction of uncolored region relative to colored region in this stream here. So like all of these chunks here are going to be, you know, utilization 0, and then like when this is around, utilization 1, average that out. So you can see we have very low utilization here as a symptom. So there's like basically 2 problems that you can read off from this trace that correspond to the 2 problems that I called out in the code itself in comments. One is we have this Python function that's like creating a class, like defining a new class and creating an instance of it. And like that's taking 13 microseconds. I see 7 microseconds. That text is probably not too easy to read for folks, but you can, if you pull up a profile, you can see it. That's maybe a little bit better. I can zoom in as well. So you can see 13 seconds on this build class, 7 seconds for the later runs. And if I compare that, yeah, let's pull this matrix multiplication here is taking 5 microseconds, 5 microseconds. Yeah, so it looks like they're all taking about 5 microseconds. So that's actually like the same amount of time that it takes Python to like define a class for doing our entire matrix multiplication. So that's bad. That's going to slow us down. Like that's adding extra overhead and adding basically an extra 5 microseconds in here. And it's looking like those gaps are what? Can we measure it? Yeah, we can measure. There's like 25 to 30 microseconds between each of these matrix multiplications, and we're spending like 5 or 6 of them like defining a Python class, which is silly. Like we can just define that class once and reuse it. But that's the sort of thing, like when you're building a more complex pipeline, you can accidentally kind of like insert a little bit of like CPU work that you don't want to include. And so going back to the code and removing that. But then the other sort of like harder problem is that if you look at just like the lengths of these matrix multiplications of like 5 microseconds, and you compare that to like how long it takes PyTorch to decide that's the kernel that it wants to run. So this is the period, that right there that I'm highlighting. That 20 microsecond period is basically Python and C++ on the host deciding which CUDA kernel to launch. And it's taking 20 microseconds. So that's also like quite a bit longer, 4 times longer than the actual kernel execution is. And it's like pretty hard to get that down. Maybe something you could set some flags, like play around with PyTorch to try and reduce that overhead. But fundamentally, like it takes some time to like figure out which CUDA kernel to use for each operation, and that's just longer than the operation that we're actually asking to execute. So the solution to this is to just like boost the size of the problem that you are executing. You can actually boost this until these matrix multiplications are like exactly as long as these, like the period that it takes for the application to like decide what kernel to run next, without taking any longer, right? There's no latency penalty if this is, if this is the only application running on the GPU. There's no throughput penalty. Like it's free. You're just like not using these resources. So that frequently means you can go back up to kind of the application layer of your problem and say, wait a second, if I ran on twice as many inputs, if I generated 4 images every time a user requested them, I would actually like I would complete in the same amount of time. It would cost me the same amount of GPU resources. I'll just do that. So in this example, it's just like scaling up the random matrix that we're multiplying, and that's like super easy. But it actually turns out that there are many cases where you can actually do this when you are running like real workloads. But the details are going to kind of vary depending on the like application and the like specific workloads that you're running. So we can actually see what that looks like. So I'm going to need to open a little file to pass some keywords arguments into this. I think the value that worked super well for me last time was like 3 or maybe 4. So we're going to scale up the problem by a factor of 4 in each direction. I'm going to pass these keyword arguments into the function that I want to run this underutilized. I'm going to give it a tag as well. So these are just like little extra features to make it easier to find files later. So I'm going to say, webinar scale up so that I always know which one it was. Keep that with stack. And oh yeah, and then path quarg JSON, I think it is. Let me maybe get the help. Oh, it's not called tag. Oh, it's called label. Yeah, there we go. Label is the name of that one, and then help is telling me quargs JSON path with debab case quargs.json. Okay, so now we're rerunning that. Oh, I wanted to also make some code edits. That would have just rerun the same code we ran previously. But I want to speed this thing up as well. So we will move that silly Python class creation out of this for loop, and great. Rerun it. So launching kernels, yeah, okay, great. Gut check, we're at now like 200 out of 400 microseconds. So the number of microseconds seems like it's roughly the same, like total execution time. But now the like fraction of time spent in CUDA is greater. Let's see if we can see that from our trace. Let's copy that. Copy that over to my downloads directory so it's easy to find and upload to Perfetto. Yeah, let's zoom back in. Let's pin the CUDA stream again. And let's zoom in on the part that we care most about, the profiler step. Oh yeah, sorry, I should have called this out. The profiler like gives some extra annotations that help you like zoom in. Like there's all this other stuff going on you can see that's like this is like wrapping the actual function.local call. Like this is modal is like calling and the profiler is doing stuff. But if I want to focus on the actual GPU execution, I want to check out this area. We can now see like that function build class that was setting up that Python class is now at the beginning. We don't see it anymore in between our calls. And now we can see we might actually be at the point, not sure. It looks like there's still a little bit of gap between executions. So I think 4x wasn't quite enough. Let me zoom out so we have a little bit more vertical space. Dropping that with stack would get rid of a bunch of this extra stack stuff. But then you would miss things like that build class. Yeah, this part here, you can see now the CUDA kernel launches are not super far ahead. Yeah, it looks like they're pretty well aligned with the actual the like PyTorch, the like host side CUDA launch kernel call and the actual execution of the kernel are still like, only separated by a few microseconds. Yeah, 1 microsecond here maybe. And so it's not, what you'd really like to see is like a very long wait as you like from when the host requests the kernel launch and when it actually runs. That means the GPU is like doing lots and lots of work while you are like moving forward on the CPU. So we don't quite see that here. We could scale it up even further and we would start to see that. But we've already seen like a major improvement, and then this will show up as high level like increase in GPU utilization. You can see there's now like a much smaller fraction of the time that we are running on, like that we are profiling. This profiler step is more like now like half of the time is spent running a kernel on the GPU, where before it was like 10%, 5%, something like that. And that is the GPU utilization metric that will show up in your modal dashboard or in NVIDIA SMI. That improvement will show up. So one last thing that I wanted to show as part of this webinar is also how to look at these in TensorBoard, because I've been kind of like guiding you on how to read these traces, but they're pretty complex. And actually, TensorBoard comes with like some additional sort of like profile level breakdowns. It includes the GPU utilization percentage. It includes some like lower level metrics like streaming multiprocessor efficiency and warp occupancy. And all of that is like useful information. And it like importantly also includes these like high level recommendations like the ones that I've been giving, which is like, oh, you have low utilization, try increasing the batch size, like try doing more work. So that's all inside of TensorBoard, inside of their like PyTorch profiler integration. So this is a nice thing to add on top of your like basic PyTorch profiler. A lot of the features that NVIDIA Nsight like includes as well. And nice thing is you can do all this on Modal. So skipping past the part where I talk about some of that like performance optimization stuff that's written into the example. Down here, we show how to like serve TensorBoard on Modal. Basically, you get the TensorBoard library, you add this plugin for handling Torch's profiler. TensorBoard has all these crazy plugins added to it. There's like only one like modal specific thing, which I'll actually get to in 1 second. Let me scroll down a bit. So the key thing that makes it easy to like host TensorBoard on Modal is that TensorBoard is a WSGI app, WSGI app. So it's similar to like a Flask app in that way, this like general, this standard style of app serving WSGI. And so all we need to do is like get inside of the TensorBoard source code, pull out the way that they construct their WSGI app, and then like, send it, like return that WSGI app. That will host the thing on Modal. But in order to give it access to our traces, we need to attach this like distributed volume here, this place where we were storing our traces. So that's one bit of like modal specific stuff, and we want to like make that our TensorBoard directory. But then sort of more like the one tricky bit here is that TensorBoard will check to see if there have been changes on the file system, but the way modal volumes work is they're designed for like write once, read many workloads. So a case where there's like very rare writes and lots of reads. And that like definitely fits with this paradigm with TensorBoard, because you like write a trace once and then you might read it like many times from TensorBoard from other locations. But the one tricky gotcha is that you need to refresh. If you want to see the like latest changes to a volume, you need to refresh. So in order to make that easy, we use this little middleware here, a WSGI middleware. That's like extra little stuff you can add to an application that runs on certain requests and like changes the behavior of an app. So I just wrote this little tiny middleware for TensorBoard that will, whenever you refresh, reload all the latest traces. So that's like this is what a WSGI middleware looks like. There's like a Python enhancement proposal that details the spec for this. And the main thing it just does is like it tries to reload the latest traces anytime you refresh, or if you opt in with this specific path. So that makes sure that you can like readily get a hold of the latest traces when you are running. So that's just like one little gotcha. So taking a look at that, let's see, the webinar one is not showing up yet, probably because I didn't hit refresh. Go ahead and hit refresh, reload, and that should reload the volume and pull up the latest one. There's a bunch of other, you can see I have a bunch of other things that I've traced here. Like as I was building this example, I traced a bunch of different ones. There's underutilized webinar scale up. This is the same one we were looking at most recently in Perfetto. Yeah, you can see GPU utilization 40%, like I estimated. You can see that there. That's still not super high. Like you would want to get it higher to like really make sure you're using the GPU. And you can usually get to those levels. So that is still the performance recommendation. But we don't just see this high level breakdown. There's like slightly like some breakdowns of the information that is also in the like printed profile. You can see we've got we can see, oh yeah, you're spending most of the time on matmul on the host. And if we look at the GPU kernels, yeah, there's only really one, this matrix multiply kernel. That's where we're spending all of our time in. So those breakdowns can be helpful for seeing like when you have a really hard problem that you need to fix up, that you need to optimize. Like you've already done the like low hanging fruit stuff that we've been talking about in profiling underutilized. We've been you've made sure that the CPU is not getting in the way. You've got 100% GPU utilization. You've got good power utilization as well. Then you need to figure out what are the bottleneck kernels and like how can I make those faster? Can I change the format of my model? Maybe write a specialized Triton kernel for that. Like that is something you can figure out from this like kernel view. It says like, oh yeah, this is the one that this is 97% of your time. This is the like the high pole in the tent. This is the one you would need to speed up. It also does have a built-in trace viewer built on the Chrome trace viewer that shows like basically the same things that we were just looking at. There are some like nice little bonus things, like you can actually see the GPU utilization in there, and also an even lower level metric, streaming multiprocessor efficiency. That's like closer to what to like, are you actually using the GPU? Are you using like all of the streaming multiprocessors that you have available? And you can see that over time, which is pretty cool and very useful. And also you can get this finer grained view of the GPU utilization. Like here, we can see that the GPU utilization is high, sort of like in the middle of this, and low on the outside. So like the bulk says like 40% GPU utilization during the entire step, but it looks like we're getting to like high, maybe 100% GPU utilization, 90 something percent GPU utilization during this fraction. And that so that suggests like, oh yeah, we could figure out some of these things on the side here, or just get more work out of the way of the GPU. But also it kind of just means like the core part where we're actually like running lots of stuff on the GPU actually is using it very well. Not just at the kernel level, but actually at the streaming multiprocessor level. So there probably isn't a ton of low-hanging fruit here to optimize, as you would expect from something that's doing matrix multiplications, which have been optimized to hell by many engineers. Okay, so that's a quick walkthrough for this example on a particular pattern for tracing and profiling GPU accelerated PyTorch programs on Modal. And so hopefully that's useful. You can copy this code, use it for your own things. Use the TensorBoard piece, use the like profiler wrapper. Hopefully these help you like make actual great use of the GPUs that you're leasing from us on Modal, that you're using on the Modal platform. Yeah, if you run into any interesting performance debugging problems, or if you want some help or tips or pointers, my DMs are open on Twitter, Charles_IRL. Come check out the Modal Slack. modal.com/Slack. That's where we do user support and answer questions. So come through there. Look forward to seeing you there and seeing what you build. Take care.
No Docker, no YAML, just Python taking flight.